Okay, so welcome back. So in the last video, we had a look at the definition of the polynomial function and explored a little bit of their properties. So recall that the polynomial function is expressed like this over here. But we only had a look at the power functions. So in this video, we'll have a look at the more on the polynomial functions and their characteristics. So let's have a look at some definitions first. So that a local maximum here is a point in which the function reaches a maximum in a certain interval. So for example, if you see this as your number line, for example, and you see that you have something like this as your polynomial function, within a certain interval, for example, over here, let me use a different color. So for example, from here to here, that's an interval. We see that over here will reach a maximum value. So that's called a local maximum. And similarly, a local minimum is a point in which the function reaches a minimum in a certain interval. So similarly, in the graph that we have drawn over here, in this specific interval highlighted in orange, we see that this orange spot over here is the local minimum here because it's in a certain interval. So this one would also be the local maximum. All right, so here's the second definition. An absolute maximum is a point in which the function reaches a maximum in the entire set of real numbers. So meaning that, okay, if we have a look at the entire space, so let me draw another picture. So let's say we have something that looks like this. We have quite a bit of hills and valleys. This point over here, which I will highlight, is the absolute maximum because it's the largest peak in the function. So that's the absolute. And compared to this one over here, this one's the local. So this one's a local, and then this one would be the absolute. And similarly, we have the absolute minimum as well, which is the point in which the function reaches a minimum in the set of real numbers R. So based on the graph that we've drawn, this one would be the absolute minimum, and then this one would be the local. Now, keep in mind that local minimums or maximums can also be the absolute minimum or maximum, but the reverse may not be true at all. So because a minimum, local minimum, is basically from a certain interval, but basically the interval could also be the set of real numbers from -infinity to infinity. All right, so let's have a look at another definition. So definition 3. So an x-intercept is a point where the function is equal to 0. So in other words, when f of x is equal to 0. So we solved polynomial equations, or basically quadratic equations before, where we basically solve for the roots of the equation. So for example, if we have something like this, so let me try. So we basically took these 2 points. So this point here and this point here, that is when f of x is equal to 0. Those are called your x-intercepts. So let's have a look at an example. So example 1 states that determine the key features of the graph of the polynomial function. F of x is equal to 2x cubed minus 4x squared plus x plus 1. And also determine, which means that we have to determine the degree, the leading coefficient, the end behavior, the x-intercepts, and the number of minimum and maximum number, and the number of local maximum and minimum points. Okay, so let's have a look at this. So the degree here, given the function as well, we would see that this 3 over here would be the degree of the polynomial function. So we would say that the degree here is 3. Now the second one is the leading coefficient, which is also given by the function, and that is simply 2. All right, so stating the end behaviors now, we have to observe what happens to the graph as x approaches negative infinity or as x approaches infinity. So part 3, we say that as x approaches infinity, so meaning that as x gets larger, so we would see that the graph on this side would be approaching infinity, positive infinity, as we go, as x goes to infinity. So f of x approaches infinity. And similarly, as x approaches negative infinity, f of x would approach negative infinity. So it would go this side to negative infinity. Okay, so part 4, we want to determine the number of x-intercepts based on the graph that is given. So let's have a look at the graph. So we see here that, okay, the x-intercepts is when f of x is equal to 0. And we see that 1, 2 points, and 3 points is where the function is equal to 0. So that means there are going to be 3 x-intercepts. Okay, so the number of maximum and minimum points, so we have to look at it from the entire set of real numbers. So we would see on the graph here that we only have one maximum at this point over here. So this would be the maximum, but it is also a local as well. So put that in brackets. And over here would be the minimum, which is the absolute, but it's also a local. So that means there are one max and one minimum. And similarly, part 6, the local minimum and maximum, in this case, would also be the same as the maximum and minimum because we don't have any other maximum or minimum. So the local max here would be 1, and the local minimum would also be 1. All right, so that's all for this part, this example. Let's have a look at another example with example 2. So let's repeat example 1, but with the function this time. G of x is equal to negative 2x to the 5th plus 5x cubed minus x. Okay, so first of all, let's state the degree and the leading coefficient. So the degree here is given by the function, which is just 5. And then the second part, we have the leading coefficient given by negative 2. And then we state the end behaviors. So as x approaches infinity here, we would see that, okay, as x gets larger, the function will just get larger negative. So that means it's going to approach negative infinity. So f of x, or g of x actually, g of x approaches negative infinity. And then similarly, as x approaches negative infinity, we see that g of x will approach positive infinity. So g of x approaches infinity. All right, so now let's have a look at the number of x-intercepts. So part 4, we see from the graph that we have 1, 2 points, 3 points, 4 points, and 5 points. So we have 5 x-intercepts here. All right, and then part 5 here, we want to determine the number of maximum and minimum points. All right, so the maximum, there's only going to be one absolute maximum here, which is going to be this point over here. So this point is called your absolute max, or we'll just call it max. So there's only one of them. And the minimum, same thing. We also have one, which is just going to be this point here. So that's your minimum. So we also have one. Now, what about the locals? So we could also have a local maximum and a local minimum as well. So these ones would also be considered as local as well. So local, and this one would also be a local. Okay, so let's see the local max here. So including the absolute, so we would have 1 and 2. So over here would be an absolute or a local here. So that's a local max. And this point over here would be the local minimum. So the number of local maximums we have is 2. And the number of local minimums is also 2. All right. So let's have a look at a couple of questions. How is the degree of the polynomial function related to the number of x-intercepts? The second one is, how is the degree of the polynomial function related to the total number of maximum and minimum points? And last one is, how is the degree of the polynomial function related to the number of turning points? So turning points is another important concept, which is basically how the function will turn based on the peaks and valleys that we have here. So it could either be facing upwards or it could also be facing downwards like that. But we'll come back to these 3 questions. But first of all, we'll do a little bit of an investigation. So let's say these 3 functions given by f of x is equal to x cubed. We have x cubed plus x squared minus 4x minus 4. And then we have the third function given by x cubed plus 5x squared plus 3x minus 9. Okay, and we have the 3 graphs that are given here. Okay, so how many x-intercepts do you see in each graph? So in the first graph that we have, we see that there's only one of them, which is just at the origin. So we would just say there's one x-intercept. Now, what about the second graph? Well, if we have a look here, 1, 2, and 3. So we have 3 x-intercepts. And then the last one, we only have 1 and 2 x-intercepts here. Now, keep in mind that all of these are cubic functions, but the number of x-intercepts will depend on the degree of the function. All right, so the next part is, how many maximums or minimums do you see in each graph? Now, here's the thing. For the first graph, this point over here is not a maximum or minimum because technically the maximums and minimums will keep on going without any peaks or valleys at all. So this point or anywhere in this cubic function here won't have any local maximums or minimums. So that means we have 0. So for the second one, let's have a look at the graph. We see that we have 1 local maximum and 1 local minimum. So how many in total do we have here? Well, we see that we have 2 of them. And same thing for the other graph. We would see that, okay, this point over here is a local max. And then a point over here is also a local min. So that means we have 2 as well. And how many turning points do you see in each graph? So from the first graph, we would see that there are no turning points here. So the turning point must be going from increasing to decreasing, or it can go from decreasing to increasing. And from the first graph, we don't see that it's increasing, then decreasing, or decreasing, then increasing. So we would say that there are none. So 0. And then for the second graph, we would see that there are 2 turning points, because you see that one is increasing, then decreasing, and then decreasing, and then increasing later on. So that means we would have 2 instances where the function is turning. And then last one, third graph, we would also see that there are also 2 turning points here. So 1 turning point here, and then another turning point there. So we have 2. So 2 turning points. Okay. So based on the graph that or the 3 graphs that we have just observed, we would see that, okay, we can have at least one x-intercept, and we can have a maximum of 3 x-intercepts. We're not exactly allowed to have 4 x-intercepts in this case, because the degree of the polynomial function has to be, it gives you the maximum number of x-intercepts that you have or may have. So like, for example, a quadratic function, you can have from 0, 1, or 2 x-intercepts, but you can't have 3 x-intercepts. Now, for the local maximums and local minimums, we would see that, okay, we can only have a maximum of 2 turning points, but we could have 0 turning points as well. Would it be possible that you could have 1 turning point for a cubic function? That's an interesting topic, but we'll save that for later. Okay, so let's say we have the cubic function now, or the quintic function of degree 5. So we're given the 3 functions. One's the base function, x to the 5th. And then we have x to the 5th plus 3x4 minus x cubed minus 7x squared, and then plus 4. And then the third graph, we would have negative x to the 5th plus x to the 4th plus 9x cubed minus 13x squared minus 8x plus 12. And below are the 3 graphs. So doing the same thing again, let's see how many x-intercepts do we see. So how many x-intercepts do we see in each graph? So if we quickly look at the graph, we would see that here's 1. So we have 1 x-intercept here. And in the second graph, we would have 1, 2, and 3 x-intercepts. And then in the third graph, we would see that we would have 1 x-intercept, 2 x-intercepts, 3, and 4. So let me write them down. So we would have 1, 3, and then 4. So with the quintic function, notice that we don't have a 5th degree or 5 x-intercepts, but it's entirely possible that we could have 5 x-intercepts. For example, it simply just has to cross the x-axis 5 times. So if we have a look at this graph, so it would look something like this. So it crosses once, twice, 3 times, 4 times, and then 5 times. So it could look something like that, as if you want a 5 x-intercepts here. So we would see that this is a quintic function, so it has 5 x-intercepts. And now we could also work with the local minimums and maximums, which we'll do next. Okay, so how many local maximums and minimums do you see in each graph? Well, once again, in the first graph, there are no local maximums or minimums here, because it's always going to be increasing. And it's not going to go increasing and then decreasing. So that means for the first graph, we would have 0. So for the second one, we would see that over here, we would have one minimum point here. So that's a local minimum. This one's the absolute max. So I just called it max. And then this point over here as well. Notice that the x-intercept is also a local minimum as well. So this would be the absolute minimum, or in bracket, I'll put local as well. So these are also local. So in total, actually one more. There's also this point over here, because it's crossing the x-axis or touching the x-axis, but then going back down. So that would also be counted as a local minimum. So that'd be local minimum. Or max, actually, sorry. So in total, we would see that we have 4 locals here. So we would write 4. And how about the third graph? Well, here we would see that we would have this point over here, this point here. There's one that's hidden over here, and there's one at the x-intercept here. So this point over here would be the max, the minimum point, which is also a local. This point over here is a maximum value, which is absolute, but it's also local. This one over here is going to be a local minimum. And then over here is going to be a local max. So in total, we would see that we have 4. Okay, so the turning points that we see in each graph, once again, the turning points has to go from increasing to decreasing or decreasing to increasing. For the first graph, we would see that the function is always increasing, so there are no turning points. So we say 0. For the second graph, we would see that there's one turning point here, there's another turning point here, another one, and then another one. So we have 4 turning points. And then for the third one, we would see that we also have 1, 2, 3, and then 4 turning points. All right. So we have the 3 functions given, or the values given. So we know that based on what we have observed, that the values can range between specific ranges. So let's have a look at a couple of make a couple of generalizations for odd degree polynomial functions. So let's say that we're given any odd degree polynomial function. So the number of x-intercepts can range from between 1, for example, if we take the linear function, and it could also go from 2 to 3 to 4 to 5, and so on, all the way to n x-intercepts. But we can't have n plus 1 x-intercepts as well. Okay, so for the second one, so let's say we're given an odd degree function, then the number of local maximum and minimum can range from 0. It could start from 0 because based on what we have from x to the 5th, x cubed, or even the linear function as well, there's going to be no local maximums or minimums. And we could also have 1 minimum or maximum. And then we could also have 2 and so on, all the way to n minus 1. So this number over here is important. N minus 1. Notice that in the graph that I drew on the side over here, that, okay, even though we have 5 x-intercepts, we have 5 local minimums and maximums. So there are 4 locals here, right? So that means there's going to be up to n minus 1 local minimums and maximums. So for the third one, we also have an turning points as well, a generalization for turning points. So for any odd degree function, the number of turning points can range from 0, as we have seen, and it can go until n minus 1 as well. So notice that part 2 and part 3 will be the same because the number of maximum and minimum points will determine how many turning points you require in a polynomial function. Okay, so let's try to use the 3 generalizations for odd degree polynomial functions and to determine the minimum, the maximum number of x-intercepts, the minimum and maximum number of local minimums and maximums, and the minimum and maximum number of turning points of a function with degree 9. So we want to focus on the 9th degree polynomial. So simply, using the 3 generalizations above, we know that any odd degree polynomial function can range from 1 to n. So since n here would be 9, so say n is equal to 9, then we would just have up to 9 x-intercepts, but a minimum of 1. So we could have 1, 2, 3, and so on until the 9th x-intercept. For the second one, so the second one here is we want to determine the number of minimums, local minimums, and maximums. So since n is equal to 9 here, we could have from 0, and then we could have 1, and then 2, all the way until 8. So 8 is the maximum number of local minimums and maximums that we could have. And then part 3 is for the number of turning points, which is going to be the exact same as the number of local minimums and maximums. So we could have 0, 1, 2, all the way to 8. So that's basically the general case for the odd degree polynomial functions. Now let's have a look at an even degree polynomial function case. So let's say we are given the set of polynomial functions of degree 4. So we have f of x is equal to x to the 4th. We have f of x is equal to x to the 4th minus x cubed minus 6x squared plus 4x and then plus 8. And then for the third one, we have x to the 4th minus 3x cubed minus 3x squared plus 11x minus 4. So repeating the steps that we just did above, let's determine how many x-intercepts there are in each graph. So for the first graph, we would see that only this point over here is the x-intercept. So we would say that there are 1 x-intercept here. Then for the second graph, we would see that there's 1, 2, and then 3 x-intercepts here. So we would say there are 3 x-intercepts. And then for the third one, we would see that there's 1, 2, 3, 4 x-intercepts. So we would say that there's 4. Okay, so same thing as before. Now let's determine how many local minimums and maximums we see in each graph. So for the first graph, this point, the x-intercept over here is also going to be your local minimum. So this is just going to be your local min. And we only have 1 of them here. So we would just say that we have 1. And then for the second one, we would see that there's one over here, and that is going to be your absolute minimum. So that's the minimum, but it could also be a local. We have a absolute maximum here, but it's also local. And then we also have this point here, which is also a turning point or a local minimum and maximum. So this one would be the local minimum. So from the graph, we would see that we have 1, 2, and 3 local maximums and minimums. So we would say 3. And then in the third graph, we could also see that, okay, this point over here is your absolute minimum. Here's a maximum. And here's a local min. So how many maximums and minimums do we see? We only see 3 of them. Now, since from the previous, from the odd degrees case, the number of maximums and minimums is the same as the number of turning points. So that means the number of turning points that we see also has to be the same as the number of local maximums and minimums. So we would have 1, we would have 3, and we would have 3. So that's basically what we have for these set of functions. So now let's have a look at the 6th degree polynomial function. This is a typo here. That should be a 6. Okay, so let's say now we're given the set of polynomial functions of degree 6. So we have x to the 6. We have 1/8 x to the 6 minus 7 over 4 x to the 4th plus 49 over 8x squared minus 9 over 2. And then the third function, we have 1/8 x to the 6th, 1/4 x to the 5th, minus 13 over 8 x to the 4th, minus 7 over 4x cubed, and then plus 3x squared. So let's have a look. So same thing again. How many x-intercepts do you see? Well, from the graph above, we would see that we would have 1 x-intercept here. So we would say there's 1 here. And then for the second graph, we would see that we have 1, 2, 3, 4, 5, 6. So we have 6. We have 6 x-intercepts here. And then for the third one, we would have, so we have 1, we have 2, we have 3. There's 1 over here as well. There's 4, and then there's 5. So we have 5 x-intercepts. So 5. All right. So now how many local minimums and maximums do we see here? Well, for the first one, we would see that there's only 1 local minimum. So that's just going to be 1. And then for the second one, we would see that we would have, so 1, 2, 3, 4, and 5. So there's going to be 5 local minimums and maximums in total. So there's going to be 5. And then in the last case, we would see that we have 1, 2, 3. There's 1 that's hidden in there, but there's 1 there. And 4. So we have 4 local minimums and maximums in total. And since the turning points is the same as minimum and maximum locals, we would have 1, 5, and 4 turning points. All right, so let's make a couple of generalizations for even degree polynomial functions. So for any given even degree polynomial function, so the number of x-intercepts can range from, so here's the thing with the even degree case. So let's say we have a quadratic function that's given like this. notice that the quadratic function can also go above the x-axis. So it could have from 0 x-intercepts, 1 x-intercept if it touches, and then 2 x-intercepts if it goes below it. And we would see that the 2 arms are touching the x-intercept. So that means we could have 0 x-intercepts to start with, and then it would go all the way until n. So that means we could have from 0, 1, 2, all the way to n x-intercepts. And then for the second one, for any even degree polynomial function, the number of turning points can range from, now for this one, there's going to be 1, that's going to be the minimum. And then it can go all the way to n minus 1, which is also the same as the odd function. And same thing for part 3, the number of turning points is also the same as the number of local minimum and maximum points. So there's going to be 1, 2, all the way to n minus 1. Okay, so using the generalizations above, let's try to determine the number of x-intercepts, the minimum and the maximum, the minimum and maximum number of locals, and the minimum and maximum number of turning points of degree 8. So since n is equal to 8 here, all we have to do is just put everything until 8. So for 1, you would see that the minimum here could be 0. The maximum number of x-intercepts is 8. And then the second one, the minimum number of turning points is going to be 1. And then the maximum number of turning points is 7, because it's going to be n minus 1. And then for part 3, it's going to be the same as the number of local minimums and maximums. So we have the minimum being 1, and then the maximum being 7. Okay, so we had a look at the two cases where we had a look at the even degree case, and we also had a look at the odd degree case. So going back to the question up here, how is the degree of the polynomial function related to the total number of x-intercepts? Well, if n is the degree of the polynomial function, so if n is the degree of a polynomial function, then the function can have at most n x-intercepts. N x-intercepts, but at least 1 if n is even, or if n is odd, or at least 0 if n is even. So that's the generalization. The true generalization for or how they're related to the number of x-intercepts. And then for the second one, how is the degree of the polynomial function related to the total number of local minimums and maximum points? So if n is the degree of the polynomial function, so if n is the degree, then the function can have at most n-1 local max and mins, but a minimum of 0 if n is odd, and or actually should be or a minimum of 1 if n is even. So that's the case for the degree of the polynomial function and how it's related to the total number of local maximum and minimum points. And then for the last question, how is the degree of the polynomial function related to the number of turning points? So once again, since the number of local minimums and maximums has to be the same as the number of turning points, so we would just say that the number of turning points is the same as the number of local maximum and minimum points points. But we had to make sure that it can either go from increasing to decreasing or decreasing to increasing. So INC for increasing, DEC for decreasing, or decreasing to increasing. Now, note that from these two cases, if we go from increasing to decreasing, so something like this, then it's going to be a local max. So this would be considered a local max. So if it goes from increasing this way and then decreasing this way, that's going to be your local max. Similarly, if we have decreasing to increasing, that's going to be your local minimum. So it's going to look something like this, and then you would just go down and then back up. And you would have your minimum over here. Okay, so now those are the three generalizations for most or all polynomial functions that we will keep in mind for later on. Okay, so we've done all this. Now the last topic that we're going to talk about for today is going to be finite differences. So we had a look at finite differences in previous years when we had a look at how if the first or second differences are constant, then it's a quadratic function. But if the finite differences you're given is not constant, then we don't know what the difference is. Not going to be a polynomial function. So the definition of finite differences is as follows. So for a polynomial function of degree n, where n is a positive integer, the nth differences are equal, have the same sign as the leading coefficient, and is equal to a times n factorial, where n factorial is given by n times n minus 1 times n minus 2 times, and so on until you reach 3 times 2 times 1. So for example, if you take 5 factorial, that's simply just going to be 5 times 4 times 3 times 2 times 1, which is equal to 120. So with finite differences, this will allow us to determine the degree of the polynomial. It will allow us to determine the leading coefficient and the sign of the leading coefficient. So if you remember, so say we are given like a table of values of x and y. To find the finite difference, so let's say we're given x1, x2, and then y1, y2, for example, then the first difference here, so we say delta y here, is simply going to be y2 minus y1 for between these two rows here. And then let's say if we have a y3 here, then the finite difference would be y3 minus y2, and then so on. But let's say we have a second difference. So we would say delta squared y, which represents the second difference. This would be the difference between these two. So we would say that y3 minus y2 subtract y2 minus y1. And then the list would just keep on going. All right, so let's have a look at a couple of examples that has to do with finite differences. So let's use finite differences to determine the degree of the polynomial function, the sign of the leading coefficient, and the value of the leading coefficient. Okay, so let's use finite differences. So we're going to calculate the previous value and the first value, the next value. So that's going to be negative 12 minus negative 36, which is going to equal to 24. And then once we have that, we could start with the next row. So this time we'll work with negative 2 and negative 12. So it's negative 2 minus negative 12, which is going to be 10. And then 0 minus 2, or negative 2, which is going to be positive 2. Then 0 minus 0, which is 0. And then 4 minus 0, which is 4. And then so on. So 18 minus 4, so that's 14. And then 48 minus 18 is 30. So from this, we know that the first differences are not constant. So we're talking about these values here. They're not constant. So we know that it's not linear. So over here, not linear. And because it's not constant, or the first differences is not constant. So that means we would also have to check the second differences. So delta squared y now, let's have a look at each of these. So we have to look at the next, we have to look at these values, how they interact with each other. So from this, we would start with 10 subtract 24, which is negative 14. And then 2 minus 10, which is negative 8. 0 minus 2, which is negative 2. 4 minus 0, which is 4. 14 minus 4, which is 10. And then 30 minus 14 is equal to 16. So we know that it's not going to be a quadratic as well. So not quadratic, because the second differences are not constant. So we have to keep on going. So that means next we have to check the third differences. So between these two, these two, these two, these two, and these two. So let's check the third differences now, which is given by delta cube of y. So from this one, we would see that we have negative 8 minus negative 14, which is given by 6. Negative 2 subtract negative 8, which is given by 6 as well. And then 4 minus negative 2, which is 6. We have 10 minus 4, which is 6, and then 16 minus 10, which is 6. Well, look at that. We have 6 in each of these parts here. So that means it's going to be a cubic function, because the third differences are all constant. So for part 1, on the side I'll do over here, part 1, the degree here is 3, because the third differences are constant. And since 6 is a positive number, or the constant that we're given is a positive number, then we know that the sign of the leading coefficient is going to be positive. And then to calculate the value of the leading coefficient, we had to find the value of a. So all we do is multiply a times n factorial. So in this case, n would equal to 3. So that means we have to calculate 3 factorial. And that is equal to the constant 6. And then solving for a. So a is going to be the value of your leading coefficient. So that is going to be a is equal to 6 divided by 3 factorial. Now 3 factorial is simply just going to be 3 times 2 times 1, which is going to give you 6 as well. So that means we're going to have a is equal to 6 over 6. So a is equal to 1. All right, so that's how we do finite differences. So for the last example that we'll have a look at, we are doing the same thing, but now we're given a different set of values. So let's start by finding the first difference. So delta y. So we have -8 subtract -54, which will give you 46. And then we do 0 minus -8, which will give you 8. And then we just keep on going with the list. So I'll just write down the numbers. You could check these. So we have 6, and then we'll have 16, and then we'll have 14. And then we have -24, and then -122. So first differences are not constant, so we know that it's not going to be linear. So that means we have to keep on going and check with the second difference now. So doing the same thing again. So we do 8 minus 48, which will give you -38. And then 6 minus 8, which is -2. 16 minus 6, which is 10. And then 14 minus 16, which is -2. And then -38, and then -98. So second differences are not constant. So we know that it's not a quadratic function. So now we check the third difference. And you would just keep on going until you find a column that is just constant. So now we do -2 subtract -38, which will give you 36. 10 minus -2, which is 12. And then -2 minus 10, which is -12. And then we have -36, and then -60. Okay, and then so third differences are not constant here. So we check the fourth difference now. So the fourth difference, so we take 12 minus 36, which will give you -24. -12 minus 12, which is also -24. And then -36 minus -12, which is -24 as well. And then -60 minus -36 is -24. There we go. Now we see that the fourth difference here are all constant, and we get a value of -24. So that means for part 1, the degree here is 4, because the fourth difference are constant. And then for part 2, we see that the value is negative 24. So that means the leading coefficient is going to be negative. And then part 3, we simply want to determine the leading coefficient, which is the value of a. So if a times 4 factorial, which is equal to the value negative 24. So solving for this, a is negative 24 divided by 4 factorial. So here, negative 4 factorial would simply just be 4 times 3 times 2 times 1, which is equal to 24. So we have 24, negative 24 divided by 24. So we would just have a is equal to negative 1. So the value of the leading coefficient is negative 1. Okay, so to conclude this lesson for today, what we have covered, we first had a look at the definitions of the local maximums and minimums and the absolute local absolute minimums and maximum values. We had a look at the x-intercepts, we had a look at how to describe where the maximum and minimums are based on the graph that is given. And then we had a look at a couple of investigations answering these 3 questions and how is the degree of the polynomial function related to these 3 concepts here. And then last thing, we had a look at the finite differences. So basically, if we have a look at the nth difference, if they're all constant, then we know that the degree of the polynomial function is going to be n. And then we could also determine the value of the leading coefficient based on given by a times n factorial. So with all that said, I'm going to wrap things up for today. So if you have any questions, just feel free to let me know. And I'll see you guys in the next lesson.